New section, new different idea. We're still solving trig equations, but this time what we're going to do is we're going to mess around with their periods. Back in 6.2, what had been happening is we were trying to get to a nice singular angle to get the job done. So we used trig identities to get to that point, and then once we got that, we just solved for the remaining variable. But in this case, what we're going to have are some trig functions where the multiple angle or a division by angle is happening, and there's really no easy way to clear it out. And as I'll show you, there's actually a pretty easier way to actually solve for the multiple angle or the change in period. So to understand what's going to happen here, let's just go ahead and recall. Let's do a little review. What did it mean to have sine of 3x? What did it mean to have sine of x over 3? How they behave differently than a normal sine function. And what changed was the period, right? A normal sine function has a period from 0 to 2 pi, meaning that from 0 to 2 pi, sine was going to do everything it was ever going to do throughout that stretch. It would just keep repeating. But something like sine 3x, we had a new period, right? The new period would be 2 pi over 3. So what this means is over the same 0 to 2 pi, right? There's 2 pi over 3, and here's 4 pi over 3. This function would actually do the same motion once, twice, 3 times. So you can already see what's happening. If I had a value and I wanted to find its, if I had some y value and I wanted to find how many times it intersect the sine x function, it would only intersect it twice over a period here. But if I took that same y value, it would be intersecting it 6 times. So because the period is either, in this case, the period is contracting, it's shorter, that means that the sine can go through more cycles, which means over a normal 0 to 2 pi period, we're getting more and more solutions. So sine x would have 2, this one would have 6. Of course, this one, the new period, when we talk sine of x over 3, right, the new period in this case would be 2 pi over 1/3, which would be 6 pi. So now what's happening is the period is getting stretched. So there's 2 pi, here's 4 pi, and here's 6 pi. So now the function is being stretched out. And so what we're hoping is that for that same y value, right now it appears that I only have one value that remains within the first rotation as everything's stretched out. So that's kind of what's happening here. As we make the period shorter or we make it longer, we're getting either more or we're getting less solutions than a normal sine curve would get in the first full rotation. Now it turns out there's 2 ways to approach this. One way is to actually use what we've learned back in chapter 5 and try to rewrite everything as a function of x and then invoke what we learned in 6.2 to solve it. That can get a little tricky and a little crazy. The other idea is to make use of the period change and use that to our advantage. So I'm going to show both methods, and I'm hoping once you see this in action, right, you're going to see, man, that's a cool trick. All right, so let's go ahead and try to change everything to x's only. So I see cosine of 3x. So the trick that we used here was that we rewrote this as the cosine of 2x, plus x. So we rewrote it as the sine of a sum. All right, and of course this became the cosine of 2x, the cosine of x, right, for that guy. And then since we are adding, right, that turns into minus sine of 2x, sine of x equals to 0. So you can already see that we've made things a little difficult, but remember our goal is to change things in terms of x. So what do we use next? Well, we got to convert that cosine of a double angle and that sine of a double angle. This one's kind of hard, all right, but let me go ahead. I'm going to use the 1 minus sine squared x for that guy times the cosine of x, and you'll see why in a moment. So we get 2 sine x cosine of x times the sine of x. This is still equal to 0. So the good news here is I now have everything in terms of x. And what we now have to do is clean this up. So we get we get cosine of x minus sine squared of x cosine of x minus 2 sine squared of x cosine of x equals 0. And if we keep looking at this, right, we have a minus, we have cosine of x, right, and then we have minus, make sure I got this right. Oops, there's a 2 there. I'm sorry, 2 and a 2. So we have 4 sine squared x cosine of x equals 0. I'm sorry, the cosine double angle is 1 minus 2 sine squared. I forgot that. And so if we look at this now, I see that cosine's common, so I can write this as cosine of x 1 minus 4 sine squared of x equals 0. And now we can invoke what we did in 6.2. I can break this up. This is the cosine of x is 0, or 1 minus 4 sine squared x is 0. So this guy, right, in the first rotation, the cosine of x is equal to 0 at pi over 2 and 3 pi over 2. We're in degree mode, 90 degrees and 270 degrees. Right? So those are the two values that make cosine equal to 0. Over here, if we solve everything and take a square root, right, I'm going to cut to the chase, we end up with the sine is plus or minus 1/2. So we basically have the 1/2 tells us that we have a 30-degree reference in each quadrant, and plus minus says that we are truly in each quadrant. So 30-degree reference, that would give us pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6, or 30 degrees, 150 degrees, 210 degrees, 330 degrees. So there would be all our solutions. So we have 6 solutions for that particular situation. That's using the old idea of chapter 5 of converting everything into x. So I can use the 6.2 idea, factor it, and break it up. So that's one way to do the problem. A lot of algebra, a lot of things going on, puts, I guess, hair on your chest, all right? Or gives you character points. But check this out, right? What I know, right, is that this is making everything shorter, right? So here's the picture of the sine. We'd have a picture of the cosine, but it's doing the same thing. So it's taking what happened and it's basically narrowing it down. So what I'm going to do is I'm going to decide, right? So let's forget about the 3x for the moment. Let's just kind of consider what angles make cosine equal to 0. Well, in the first rotation, right, the values of theta that make that happen are pi over 2 and 3 pi over 2 respectively, right? Kind of back over to here. But since we know this is shortening the period, this is basically in the first rev. Let's go a second rev and a third revolution, right? So in the first rev we have these. In the second rev we would just have to keep adding 2 pi, and so we'd end up with 5 pi over 2, right, and 7 pi over 2. In the third rev, if I keep adding, we'd end up with 2 pi. That's what would that be? Yeah, 9 pi over 2 and 4, that's 11 pi over 2. So I'm just adding 2 pi, adding 2 pi, adding 2 pi, adding 2 pi, which is 4 pi over 2 if you want to go there. All right, and so the reason I did that is because we know, right, what's going to happen when we eventually divide the period by 3, right? I eventually have to divide all x values by 3, which collapses everything. So check this out. I'm going to now go back, and this theta, I have 3x equals pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, and 11 pi over 2, right? So I'm going back. I kind of use a substitution to analyze what I had. I went out 3 periods since I know our period is changing by a factor of 1/3. So then I went back and substituted what theta is, and to solve for x, right? Because remember, when I eventually want to solve for x, I'm going to multiply by 1/3, which means I have to multiply everything on this side by 1/3. So over here, the 3's cancel out, leaving us with x. If I multiply everybody by 1/3, well, pi over 2 times 1/3 is pi over 6. 3 pi over 2, 1/3, 1/3, 1/3, 1/3, 1/3. I'm multiplying everybody by 1/3. But the 3's will cancel out, leaving us with pi over 2. Here we get 5 pi over 6, 7 pi over 6. 3's cancel out, leaving us with 3 pi over 2. And over here we end up with 11 pi over 6. And lo and behold, when you match this up, there's the pi over 2 and 3 pi over 2, which matches what we got there. Right? Pi over 6, 5 pi over 6, 7 pi, and 11 pi, well, that matches all those guys over there. So what I'm doing is just making use of the fact that I know, right, that because of the period change, things are getting squeezed in. And since they're getting squeezed in, what I'm going to do is go out, right, since we're squeezing in by a factor of 3, that means I'm actually having that action 3 times over a normal period. So if I take those actions over 3 revolutions and then divide by 3, that basically collapses all the solutions from essentially 0 to 6 pi down to 0 to 2 pi. And that's basically the trick. So you choose what you want to do. I would actually advise you, if you have time, do both so you can kind of verify one to the other. This is really good algebra practice, and this is just kind of a shortcut. You'll be seeing me use a shortcut pretty frequently because it's nice. Okay, so here we know the period is, the new period is 2 pi over 3. So I actually have to go 3 revolutions out to accompany what's happening with the collapsing or the compression that's going to be going on. Right? So there's the trick. You'll see me use it in some videos coming soon.